In this video, I'm going to be going through civil structures, which is chapter 1 of the HSC Engineering Studies course. I've already taught everything here. I have told myself that I'm not going to look at Facebook for or any of my pictures. I'm going to paint word pictures for all of this stuff. If there's anything here that you don't understand, you need to write a note and then go and ask your teacher or contact me or look it up. Okay, so first of all, what we've got is we've got the historical implications aspect of the course. So for historical developments of civil structures, I recorded several videos, more than an hour, probably 2 hours worth of videos on bridges. Any student I've spoken to who watched these videos said they're pretty hard to watch. My advice to you is watch it at double speed if you want to learn more about the historical development of civil structures. The reality is what you probably need to know is you need to know that dead trees and timber bridges were the first step in the development. Then stone arches. Stone arches have advantages that they don't burn, they don't rot, right? They don't get eaten by termites. They tend not to be washed away. We attribute that to the Romans, the stone arches. After that, we then have things like trusses. We need to know the development of trusses. We need to talk about suspension bridges. There are very old suspension bridges, but we're talking about things like the Brooklyn Bridge and the things that came after that. Then we have cable stay bridges. That's pretty much concrete box girders being the most common bridge used these days. That's the sort of level of understanding you need to have. If you don't have that level of understanding, you need to go and do some reading. Maybe watch my video at double speed. There is a way that you can actually watch YouTube videos at faster than double speed. Okay, moving on. Engineering effect on people's lives. I think I made you do some homework on this. We had to talk about the benefit, but we always like to focus on social, economic, and environmental. There's a social benefit of being able to get to, of cutting half an hour off your drive, right? That you can go and play football with the kids. You are just less likely to get in a fight. You can be more productive. You can spend more of that time at work. Whole bunch of benefits of just reducing travel time. But there's economic impacts, right? We spend less fuel. People can deliver more goods, right? So truck drivers can deliver more goods. Then there's the safety benefit of bridges. One of my first jobs as a professional engineer was working on level crossings, and those level crossings were being introduced in the South Coast because they had accidents where people had crossed, tried to beat the train, to race the train, and been injured, and bridges prevent that from happening because there's a physical separation between pedestrians and cars and the trains. Okay, we've talked about the development of materials over time. So we talk about early alloys. We just mentioned timber, how timber is dead tree that has been cut and treated. After that, we go to stone. We talked already about the benefits of stone, and Pont Neuf being the oldest bridge in Paris, even though it's called the New Bridge. It's called that because all the bridges that were there before burnt down or washed away or got eaten by termites. Okay, after stone, we have iron bridge. When the guy built Abraham Darby III built iron bridge, people said it's not enough bridge. It's never going to work until all the other bridges got washed away, and they're like, oh, maybe there's future in this iron bridge. Not long after, they went to wrought iron and steel bridges. After steel bridges, we have more advanced technologies which are being used in modern cable stay bridges and modern suspension bridges. There's a documentary, not even a terrible video made for me, that's in your Google Classroom, which talks about the Brooklyn Bridge video talks about the quality of steel and the importance of inspecting the quality of steel and how there needed to be sufficient factor of safety. We'll talk about that later to take into account corruption. People trying to make money by selling substandard products. A real problem in civil structures today. My friend Disco, he works in construction law, he says that when he was doing his construction law degree, that a huge number of cases before the High Court of Australia are construction-based. Someone in my building is suing someone else in my building because of construction defects right now. So, environmental implications, I just set this for homework. Really what I wanted you to do was to compare timber, concrete, and steel. Of course, this is where I have to mention the sand podcast, Changed My Life. You can learn about exciting things like sand pirates. It's not just in Avatar. But the fact is, sand is a real problem. Concrete produces 8% of the world's CO2. Steel is mostly recycled, but it is non-renewable. I also showed people recently a video that did the rounds on the internet a couple of weeks ago about a guy who said that you can grow concrete. Can't grow concrete. So, moving on from, that's our first section. Moving on from that, we're going to look at trusses. Trusses are arguably the most important part of the course, right? They are, after drawings, so I've shown you that isometric drawings are in every single paper. As long as the engineering studies course has existed, more than 20 years now, there has been an isometric drawing, a threaded, just said isometric. I'm not going to go back. There has been orthogonal drawings. A threaded orthogonal section has been. I'm so angry. A threaded orthogonal section, and then I'm like, the more I get angry, the more it needs to be edited. But yet, I'm not going to edit. I'm just going to keep going. There has been one in every test. I didn't go back past 2000. I'll tell you, drawings used to be a much bigger part of the course when I did the HSC pre-2000. Okay, after that, the next thing that is most likely to be in the exam is trusses. Trusses have not been in every exam, right? I had one year who got very upset with me when there was no truss in the exam, but they have been in 90% of HSC exams. And even if there's no truss, there will at least be a reaction question worth 2 marks. Right? So there's always going to be something. Now, I am just going to say to you, you need to know how to use the method of sections. I do have a video specifically talking about the method of joints that I released after the shock of the 2021 HSC asking specifically for method of joints. That said, most of the students who answered the method of joints question, more students did well in the method of joints question than the method of sections question, which really surprised me. Moving on to bending. My students know that I like to believe that I brought bending back. I won't go into that in any more detail than that, but just to say that I believe that bending is the most important skill for civil and mechanical engineers. What you need to know is you need to know at the very least, you need to how to calculate the maximum bending moment for a simple beam. When I say simple beam, a symmetrical beam with a single point load in the middle, right? If you can't do that, you're going to have a bad time, right? That's the sort of thing we expect to see in HSCs. You also should be able to figure out where the maximum bending point is going to be. Just by looking at it, you should be able to guess where the maximum bending moment is going to be. Now, better students who know that they're looking for marks over 90, you need to be able to calculate the bending moment of more complicated beams, but not ones with UDLs. You need to know about UDLs. You need to be able to recognize bending moment diagrams with uniformly distributed loads. We'll talk about that in a second. But what you need to do is you need to be able to, if you want to get more than 90 in the subject, you really need to be able to calculate maximum bending moments. Okay. It says here in the syllabus very specifically that they can only ask you questions about simply supported beams involving vertical point loads only. Now, there's simply supported beams means that they only have 2 reactions. Well, it either needs to be a pin and a roller, or it needs to be one fixed reaction. That's the definition of a simply supported beam. The HSC question we got last year in 2021, it had 2 fixed reactions, which I think goes against the nature of what that just says there. However, you could still solve it as though it was simply supported. It's a little bit complicated. I didn't like that question. That's why I thought it was a very difficult question. But plenty of students thought that, I answered it fine, which means I probably was overthinking it. Okay, uniformly distributed loads. You need to understand the concept of uniformly distributed loads. Also, in my videos, I've talked a lot about punching shear and stirrups. This is not really something that's in the syllabus. That's why it's in red. But there was a question maybe 3 years back. It was the last question of the paper, which talked about, it asked, why do we use bending moment diagrams and shear force diagrams? And being able to understand how we reinforce diagrams is important. So that's something I have talked about. Okay, then we've got stress and strain. Now, stress and strain, we mostly taught this in term 2, chapter 2 of last year. So if you go and look at my notes of chapter 2 mechanics of last year, I don't remember what the picture is. I think it's the friction test, the coefficient of friction tester. If you go and look for those notes, you should be able to find my stress strain videos. That said, what do you need to know? Well, first of all, you need to know that we use a test called a tensile test, and the tensile test produces stress strain curves, right? We need to know that there's an elastic range and a plastic range in those tests for most metals, right? Other materials might just be all elastic, right? So glass is very brittle. You need to understand these terms. Brittle, you need to know the term stiffness. You need to understand what toughness is. Toughness is the area if you shade underneath the curve. If you've done calculus, you should understand what that concept, what I mean by the area under the curve. Now, what do we need to understand? Well, first of all, we need to know compressive and tensile stresses. Right? So these are both called axial stresses. These are stresses that run along the length of the member that we're testing. Right? If we squeeze it, it's compression. If we stretch it, it's tension. Now, there's also something called shear. Now, shear is much harder to define. Shear is when we have parallel layers sliding past each other. Typically in a beam, shear happens where we have a force that's being applied perpendicular to the beam. Right? That's typically where we see shear in a beam. Now, the formula for shear is exactly the same as the formula for everything else. It's stress equals force over area. But in year 12, we introduced two new concepts to shear. We introduced the concept of, not only do we learn about shear force diagrams, we learn about two new concepts. We learn about ribbon shear and we learn about bolt shear. Now, the idea with bolts is that when we have a bolt being pulled into two directions, we call that simple shear. If we just have one bolt joining two pieces of metal, that's simple shear, because the bolt is only being cut at one location. But if we instead have three pieces of metal joined by a bolt, now we're going to have double shear. Now, we can have quadruple shear, we can have triple shear and quadruple shear, but typically, if you don't know what I'm talking about right now, chances are you should put down double shear, but you need to figure out what double shear is. The next concept is ribbon shear. Ribbon shear is when you need to punch a hole through a piece of metal, right? When you need you have a shape that you want to cut out of a piece of metal, and you just use a big hydraulic punch, and it punches out that shape. Now, what we use there is we use the perimeter to calculate the cross-sectional area. In both cases, what we need to find is the cross-sectional area. But with bolt shear, we take the cross-sectional area, the circle of the bolt, and we multiply it by how many times the bolt is being cut. Double shear, we'd multiply it by 2. For ribbon shear, we take the perimeter and we multiply it by the thickness of the material. If you don't know what I'm talking about, go and watch those videos. There's a video of me standing in front of the board where I talk about every concept I'm talking about here. Okay. So the next concept we have is engineering and true stress. All the diagrams we see are engineering stress. However, nerds, scientists, they don't want to know the truth, and they do true stress. We need to know the difference there. If you want to find the video there's a video of Jack Nicholson and a few good men saying, you can't handle the true stress, right? So it's got a red line and a blue line. Go and click on that, and you'll find out more about that. Okay, we also talk about yield stress, proof stress, toughness, and Young's. I'll just stick with that. Okay, typically, what we're going to use in our diagrams is we're going to have either definite yield, or we're going to calculate proof strengths. And we're going to use these values to calculate the working stress. The working stress is what's used for the factor of safety. Okay, the idea is we don't use the maximum stress on the graph. Instead, we use the point where it stops behaving elastically. We know when things are behaving, now, there's also a term behaving proportionally. Behaving proportionally is the part where we're still in the resilient range, where the line is a straight line. It has a single gradient, right? A single gradient. The rise over run is equal to the stress over strain. Now, I've already recorded this once before. I know that Young wasn't the first person to come up with this, so it's Young's modulus of elasticity with a capital E on the formula sheet. The capital E is for elasticity. I think it actually might have been Euler who came up with it, and Euler has so many things named after him that they often name things after the second person who extended on Euler's work. Or Euler, all right, it's also pronounced. Okay, so we've got yield stress, proof stress, toughness. Toughness is the area under the curve. Young's modulus is that gradient that I talked about. The Young's modulus of elasticity with a capital E is equal to stress over strain. The rise over run, stress over strain. I've got a video where I go into all of this in detail if this is not sounding familiar. Now, you need to know that it's also equal to flee. E equals flee. If that doesn't make sense for you, go and read the book and see how you can create a formula of taking Young's modulus equals force times load divided by brackets extension or change in length divided by cross-sectional area. Now, If you're using true stress, you've got to use, those numbers might change a little bit, but I'm not going to go into that here. Okay, Hooke's law is sort of the baby version of Young's modulus. The idea that things stretch proportionally as we add additional load. Right? I use the analogy of my dad snapping and telling me to get out of the car. Engineering applications of all of these things, we can use these diagrams to make good predictions about whether or not things are going to be strong, whether or not things are going to resist impact. All of those sorts of main thing that we're interested though is in the yield stress. The one exception from this is that if you need to punch a hole through something, we don't care about yield stress, right? If we need to punch a hole through something, it doesn't matter if they say, I give up, I yield. No, if you're going to punch a hole through something, you care about their ultimate strength, right? Because they're going to keep fighting if you're going to punch a hole through them, right? If you don't give them an opportunity to retreat. Okay, factor of safety. So the short version is factor of safety is if I have a ladder and I design the ladder to hold a weight or a person of 200 kilograms or 2,000 newtons, well, I put a sticker on there instead that says supports only 100 kilograms. Why? Because I want to give a factor of safety of 2. And that's very common for there to be a factor of safety of 2 in engineering. Why? Because, you know what? We don't know the exact forces. That person might think that they're 100 kilograms, but they're really not. We think we understand the metal, but we really don't. You know, we don't know every atom that goes into the metal. We're using imperfect understandings of inconsistent materials. So we make our best guesses and we add a factor of safety, right? We halve the amount of load that can be applied, right? Now, it's worth mentioning when we talk about aeronautical that the factor of safety is lower for aeronautical, not because we care less. The factor of safety is lower because of economic factors, and we compensate for that low factor of safety by doing increased testing and maintenance. Okay, stress strain diagram. I don't know why that dot is there because I've already mentioned that. Like it's bad formatting, but I didn't write the syllabus. Okay, apply mathematical methods. Okay, well the whole point is this is where the maths is, right? The scumbag engineering teacher, engineering professor meme, where he says, yeah, not much maths in the course almost entirely maths, right? This is where we've seen a lot of maths. The next test we're going to be doing is going to be entirely maths. The next thing we do after we finish this lesson is we're going to start the maths for chapter 2 for transport. Okay, testing materials. I've already talked about the all-important tensile test, right? We determine the properties of metals by doing a tensile test. We determine the properties of concrete by doing compressive tests. That's how we check to make sure that shoddy developers haven't cheated on the concrete. That's how we make sure that the concrete in our buildings is strong enough and the buildings don't collapse. Now, we also have specialty tests for concrete like slump tests, right? We've talked about these and that they're used for checking the workability of materials. Engineers who are working in labs or scientists, they use transverse beam tests where they make a concrete beam and they test it under real world conditions, right? But in a lab. So they're the main concrete tests. Concrete tests, actually, this one here. Okay, specialized testing materials. Okay, so it's got X-rays. X-rays are a way that we can see the quality of welds. We can also use gamma rays, which are even stronger, right? Hulk's strongest there is. He can beat up all the X-Men. Hulk is green because he got transformed with gamma rays. We also learn about inspections like dye penetration tests. We learn about eddy current tests. All of it is in that same picture with Sam Rockwell, where we learn about hardness tests, obviously. We learn about impact tests with IZOD. All of those tests, I just teach you all the tests now, so that way I can revise them when we see them in the syllabus further down the road. Okay, testing of concrete we just talked about. Crack theory, right? What is the one rule that you need to know for cracks? If you've got a crack, what do you do to stop it from growing? Sorry? Drill a hole is exactly right. You drill a hole and that stops crack propagation. Now, in the other video I spent quite some time talking about when I first met Copeland. I talked to him about the things that the opinions I formed of him based on reading his textbook. And one of the things I said is that he really likes ladder questions, which he does, which he agreed about. And I said, you really like crack theory? And he says, oh, not really, but it's 4 pages because it's so much of the syllabus is specified. Now, I do not like teaching crack theory. This is why I outsource it to people smarter than me. I write notes and I refer you to better people's notes than mine. And I ask you to do homework so that way I know that nothing is being missed. Because this is one of my areas of weakness and I compensate for that by saying you need to go and read first-hand sources. This is the time where you actually need to read the book. But if you only learn one thing, drill a hole. Right? Most of the HSC questions say drill a hole. Ceramics. Okay. I mentioned the Aphex Twin song "Window Liquor." Vitrification is when we turn bricks from soft clay into hard clay. When we fire it, that's called vitrification, right? And I talk about the word lèche vitrine, means to lick a window. Window licking in English usually means people who aren't very bright, but in French it means people who go window shopping. Okay, so what are the ceramics we're interested in? Well, we're interested in glass and brick. Glass and brick. There's cement, but when we're talking about cement, what we're really talking about is composite materials. We're going to talk about that in a second. Okay, so glass and brick are very important engineering properties. I mentioned that there's a good podcast on brick that nobody ever listens to. We talk a lot about glass. We talk about laminated glass and toughened glass, and we talk about a couple of others in the picture of Ariel. Okay, composites. We know that all timber is a composite by definition. We learn about engineering timbers, right? Glue lambs like LVLs, plywood, chipboard, right? You should be able to talk meaningfully about those things. You should be able to write 100 words differentiating those things. If not, look at my notes. I'm actually really proud of my composite notes. There's a lot there. Concrete. I have asked you the same way that I'm not super confident about crack theory, even though I did a civil engineering degree, precast and pre-tensioned and post-tensioned concrete is tough, and that's why I give you a heap of notes, right? High quality notes, and I do explain it a little bit, but I want you to go and read these ones. This is one you really need to look at because it's hard. I have all the past HSC questions on Google Classroom for that. Okay, asphalt. We talked about asphalt in some detail in Google Classroom. It's used I would say it's getting into the personal public transport aspect, building roads, right? To me, even though that's a civil thing, I don't know, it's kind of on the borderline. Asphalt is really important engineering material. We've talked about the properties that make it a good engineering material. We also talked about how it's the most recycled engineering material. We talked about laminates and how laminates, we're going to talk about laminates a lot more when we get to aeronautical, where we learn about glare and other FMLs, metal matrix composites and those sorts of things. Geotextiles, really important to prevent erosion. Geotextile fabrics, also really important for drainage. I went into this a lot more detail when I recorded this previously, but I'm just going to say geotextile fabric, really important for drainage, right? If you don't have good drainage, if the foundation gets flooded, well, you can have your basement get flooded, and that's not good. I would hate it if I went to my basement tomorrow morning and found that my car had been flooded, right? And it's also not good because if you have a clay soil and you get too much water in the soil, that's not good. Not part of the HSE course, but if you don't have good drainage, everything built on top of the soil is in jeopardy. Okay. Explain the properties produced by composite materials. I'm really happy with my composite notes, right, in Google Classroom. Again, same thing I've already talked about, pre-tensioned concrete. Corrosion. Okay, so I have my picture of the rust monster, right? Do you remember I called my Pokemon Corrodor, right? Corrodor has 3 attacks. What are his attacks? Okay, so it's galvanic attack, right? Galvanic attack, also known as dissimilar metals. He has stress cells and he has concentration cells. That's his 3 attacks. You need to know these. When we talk about dissimilar metals, right? Dissimilar metals, which one tends to rust? The expensive one or the cheap one? Or more accurately, the cathode or the anode? Okay. Remember we had the picture of Rad Cat and Angry Ox? Which one rusts? The Rad Cat or the Angry Ox? Think of the pictures, right? That cat, did he look like he was rusted, or did that ox look like he was rusted? The angry ox is rusted, yeah? Okay, so the oxide is where it rusts. Okay, the Rad Cat, he was standing next to expensive materials, gold, right? So gold does not rust. Gold, it tends to be the cathode end. Now, they will give you a galvanic series. If you don't know what a galvanic series is, you need to ask a teacher, right? But when they'll provide you with a galvanic series, and they'll usually put gold on there somewhere, and they'll usually put zinc on somewhere. So zinc is the anode. the anode of the anode end. There's always arguments like platinum and magnesium and other ones that could be on this series. But if you can find gold, that's the cathode end, because they have to give you the series. They don't have to label the series. The question 20 last year in the 2020 HSC was on this. Was on galvanic attack. It was a good question. Okay, the next thing we need to know about is so. Dry corrosion is a thing. I don't think I've ever seen a HSC question on it. We're not going to worry about it. Okay, stress cells. If you have a scratch in the paint, we're going to have more oxygen at the top of the scratch, and we're going to have less oxygen at the bottom of the scratch. So when it fills up with water, we're going to have a corrosion cell happening. Right? We're going to have a redox reaction taking place. So which rusts, high oxygen or low oxygen? Think of Angry Ox and Red Cat. Right? Which one's got low oxygen? The cat or the ox? Angry Ox or Red Cat? The Angry Ox has poor quality oxygen, right? Low oxygen, right? That's where the rust takes place, where there's low oxygen. Okay, we can also have stress cells, right? Lots of things cause stress cells. Work hardening, if it's not properly annealed or normalized, it causes differentiations in stress. Bolts, welds. Welds are the big one. Welds can cause differences in stress. Which rusts? The stress. Which one's the anode? The stress part or the unstressed part? The stress. The Angry Ox is the part that rusts. Okay. Lastly, we're going to talk about how do we protect from corrosion? There's three main ways. We're going to protective layers, right? Everything from hot and cold dip galvanizing, chrome plating, painting, nickel plating, right? All of those ways that they're just protective layers. We can use ICP, where we add electricity to a structure, so that way the electrons that are lost through the reduction process are replaced. Or we can use on boats. What do we use? Sacrificial anodes, right? Blocks of metal that we attach to the boat, and that they rust instead of the boat. Okay, I just set homework on recyclability materials. Like I said, you should be able to be able to meaningfully compare. And this is a good question. I say this now thinking this is a kind of question I'm going to put in a trial, right? Compare the recyclability or the engineering suitability of timber, steel, and concrete. Okay. Finally, I'm just going to wrap up very quickly. The bell's about to go. Communication, right? You need to know the Australian standard, right? I've given you lots of resources on understanding the Australian standard. You need to know orthogonal threaded sections, right? They have been in every paper for 21 years. There's no reason to think that there won't be one next year. Now, they might only be worth 3 marks, but they're going to be there, right? You need to know about what sort of line thicknesses to use for your center lines, how to hatch. You need to know about bolts, right? The dimensions of bolts. You need to know about third angle projection, right? You need to know about things like PCR, so the advanced rules of things like pitch circle radius, pitch circle diameter. You need to know about what to section, right? We don't section thin sections like webs. Okay. We need to know about how to do graphical solutions. So last year I talked about 3-force method. We also have how to calculate bending moments using bending moment diagrams. I've taught you how to use CAD. You've all written an engineering report, and you've all worked collaboratively. We're done.